Welcome to Math on Ice, June 2017 Integral Equations Part B and C. There are 4 questions, 2 questions from Part B and 2 questions from Part C. The first question, suppose x is a continuous function and x of 0 is equal to 0. It satisfies this inequality. Then we have to find the range of x of root 2. Now we solve the problem by Leibnitz rule. X of t the whole squared is less than or equal to 2 plus integral 0 to t x of s into ds. Just consider the equality case. X of t the whole squared is equal to 2 plus integral 0 to t x of s into ds. So take the differentiation 2 times of x of t into x dash of t, which is equal to integral 0 to t x of s. So taking differentiation with respect to t will make this 0, and then plus differentiation of t is 1 into x of s differentiation will give you x of t. We differentiate the upper limit, and then wherever s is present we have to substitute t, right? So x of t minus 0. So this implies 2 into x of t into x dash of t is equal to x of t, and then that is x of t will be equal to 1 by 2. Now integrating, we get x of t is equal to 1 by 2t plus some constant c1. Now this constant can be evaluated by the initial condition x of 0 is equal to 0. X of 0 is equal to 0, which is equal to 1 by 2 into 0 plus c1. So c1 is equal to 0. So the final answer x of t is equal to 1 by 2 into t. X of t is equal to 1 by 2 into t. X of root 2 is equal to root 2 by 2, which is equal to 1 by root 2. So 1 by root 2, here x of root 2 10 comma infinity is not having 1 by root 2 in this range, so this is false. And this option is also not having 1 by root 2, so this is also false. We have to verify whether one or second, first option or second option. So we will just substitute this x of t is equal to 1 by t into t plus c1. Let me take it as c itself. In this equation we will have it as x of t the whole squared is equal to, I'm considering the equal to case, plus 2 times of integral 0 to t x of s into ds, right? And we got our x of t is equal to t by 2 plus c. So this will imply t by 2 plus c the whole squared is equal to 2 plus integral 0 to t s by 2 plus c into ds. So this will give us t by 2 plus c the whole squared is equal to 2 times of plus. When you integrate this will give you s squared divided by 4 plus cs. The limit is from 0 to t by 2 plus c the whole squared is equal to 2 plus, when you substitute the upper limit, when you substitute lower limit it is fully 0. When you substitute the upper limit, it is t squared by 4 plus ct. Is solving, t squared by 4 plus c squared plus 2 times of t by 2 into c is equal to 2 plus t squared by 4 plus ct. T squared by 4, t squared by 4 cancels each other. Here 2 and 2 cancels each other. Ct and ct cancels each other. We get c squared is equal to 2. C squared is equal to 2 means we get c is equal to plus or minus root 2. C is equal to plus or minus root 2. So eventually we get x of t is equal to t by 2 plus root 2 or minus root 2. X by t by 2 plus root 2. And this is what we get x of t as. Now, if I substitute x of root 2, what will happen? This will give me, because we need to find x of root 2, right? We need to find x of root 2. When I substitute x of root 2, it is root 2 by 2 plus root 2, which is equal to 1 by root 2 plus root 2. So 1 by root 2 plus root 2, this is 1.4 and 4, 1 by root 2. When you solve, when you just divide and add, you will find 2.121 is the solution. 2.121 is greater than 2, but in the first option, the range is from 0 to 2, so this is not possible. This is the possible case. So only option B is the correct answer. Next question from part B. Let phi of x be a solution of integral 0 to x e to the power x minus t, phi of t dt is equal to x. Then phi of 1 equals to. Now integral 0 to x e to the power x minus t into phi of t dt, which is equal to x. We solve the problem again by Leibniz rule. So when you differentiate the RHS, it will be equal to 1. And when you differentiate the LHS, it will be integral 0 to x, differentiation of e to the power x minus t. That will give you e to the power x minus t. Again, with respect to x, I'm going to take the differentiation. So into phi of t dt and then plus differentiation of the upper limit is 1, and then substituting wherever substituting x wherever t is there, e to the power x minus x phi of x, lower limit is 0, so minus 0 into differentiation of x is 1. So this implies integral 0 to x e to the power x minus t into phi of t into dt plus phi of x is equal to 1. Now this part is actually equal to x, right? Integral 0 to x e to the power x minus t phi of t dt is equal to x plus phi of x is equal to 1. So we get phi of x is equal to 1 minus x. When I substitute phi of 1, that is x is equal to 1, I get phi of 1 is equal to 1 minus 1, which is equal to 0. So the second option 0 is the correct answer. Next question, let y of x be the solution of the integral equation y of x is equal to x minus integral 0 to x xt squared into y of t dt. We solve the problem by the method of resolvent kernel. R of x comma t comma lambda is equal to summation n is equal to 0 to infinity lambda power n k n plus 1 of x comma t. K n plus 1 of x comma t can be evaluated from the formula, which is equal to t to x k of x comma z into k n of z comma t into dz. So, and finally we get the solution y of x is equal to f of x plus lambda times of integral a to x, that is here it is 0 to x, r of x comma t comma lambda into f of t into dt will give you the solution. Now we will find one by one k1, k2 and all. K1 of x comma t is equal to k of x comma t is equal to, we get it as xt squared, and we have lambda is equal to minus 1. K2 of x comma t is equal to integral t to x k of x comma z, that is x z squared into z t squared into dz, which is equal to x t squared can be taken outside, z cube, integration of z cube is z power 4 divided by 4, lower limit is t and upper is x. So we get it as x t squared x power 4 minus t power 4 divided by 4. This is what our k2 of x comma t is. And then we solve for k3 of x comma t. K3 of x comma t is equal to integral t to x z squared as it is. Now this part will become wherever x is present, we have to substitute it as z, right? Z t squared into z power 4 minus t power 4 divided by 4 into dz. We will take all the constant terms outside. X t squared can be taken outside. Integral t to x z cube into z power 4 minus t power 4 divided by 4 into dz. Now how do we solve this term? Z cube into this part, which will give you z power 7. This will give us is xt squared integral t to x z power 7. We'll take 4 also outside, z power 7 minus z cube into t power 4 into dz. And integration of this will be xt the whole squared by 4, z power 8 divided by 8 minus t power 4 z power 4 by 4. The whole thing, lower limit is t, upper limit is x. So this will give us xt squared by 4. When you apply the upper limit, we get x power 8 divided by 8 minus this part will be x power 4 t power 4 divided by 4 minus when you substitute t here, this will give us t power 8 by 8 minus t power 8 by 4. So we have this part to be xt squared by 4 into x power 8 by 8 minus x power 4 into t power 4 by 4 minus this part will give us t power plus t power 8 divided by 8, right? So this is xt squared by 4. 8 can be taken outside. This is x power 8 minus 2 x power 4 t power 4 plus t power 8. So this is equal to xt squared divided by 4 into 8, and this is x power 8, that is x power 4 the whole squared. So we get x power 4 minus t power 4 the whole squared. So k3 of x comma t is equal to xt squared. You take 2 here, and the remaining 16 can be clubbed with this one, x power 4 into t power 4 divided by 4 the whole squared. So what is here? So we have got k1 of x comma t is equal to xt squared, k2 of x comma t is equal to xt squared into x power 4 minus t power 4 divided by 4, and then we have k3 of x comma t is equal to xt squared divided by 2 into x power 4 minus t power 4 divided by 4 the whole square. So the general condition will be x Kn of x comma t is equal to xt square divided by, here we have 1 factorial, here we have 2 factorial, that is n minus 1 factorial into x power 4 into t power 4 divided by 4 the whole power n minus 1. So for k n plus 1 of x comma t, this would be equal to xt squared by n factorial into x power 4 minus t power 4 divided by 4 the whole power n. Now resolvent kernel r of x comma t comma lambda, lambda is equal to minus 1, so that will give you summation n is equal to 0 to infinity minus 1 the whole power n into xt squared divided by n factorial into x power 4 minus t power 4 divided by 4 the whole power n, which is equal to, you can take the terms independent of n outside, xt squared summation n is equal to 0 to infinity minus 1 the whole power n divided by n factorial into x power 4 minus t power 4 divided by 4 the whole power n. This is the exponential function, so we get e to the power minus of x power 4 plus minus t power 4 divided by 4 into this xt squared outside, so xt squared outside, so we get xt squared into e to the power minus of x power 4 minus t power 4 divided by 4. So what is our function? Y of x is equal to f of x. The question we have, f of x is equal to x. So we have x here, x minus integral, the limit is from 0 to x, integral 0 to x. Our resolvent kernel is xt squared into e to the power minus of x power 4 t power 4 divided by 4 into f of t dt. F of t is t into dt. So we have this y of x is equal to x minus, terms independent of t can be taken outside. You can take x outside. You can take e to the power minus x power 4 by 4 outside. So you'll be left with integral 0 to x t cube into e to the power t power 4 by 4 into dt. We need to evaluate y of root 2, y of x at x is equal to root 2. So we need to evaluate y of root 2. We need to find y of root 2. Right, y of root 2 we need to find. So this is y of x is equal to, when you take this t power 4 by 4 is equal to some u, we get du is equal to 4t cube by 4 into this 4 as it is. 4, this will be this 4 as it is. 4 t cube divided by 4 into dt. So 4 cancels each other. We get t cube into dt is equal to du. T cube into dt is equal to du. So x minus x into e to the power minus x power 4 by 4 integral 0 to x. So we have to change the limit also. If t is going to 0, we have u going to 0. So integral is going to 0. And then upper limit is when t is moving to x, our u will be moving to x power 4 by 4. This t cube into dt will give you du, and e to the power t power 4 by 4 will give you e power u. So it is y of x is equal to x minus x into e to the power minus x power 4 by 4, and then integration of e power u is e power u itself, e power u 0 to x power 4 divided by 4. So y of x is equal to x minus, so when you substitute x power 4 by 4, x minus x e to the power, here x power minus x power 4 by 4 e to the power x power 4 by 4 minus e power 0 is 1. So we get y of x is equal to x minus x into e to the power minus x power 4 by 4 into e to the power x power 4 by 4 minus into minus plus x into e to the power minus x power 4 by 4. And these two powers add together and we get 0. E power 0 is 1. So y of x is equal to x minus x plus x into e to the power minus x power 4 by 4. You can cancel these two. So it is x e to the power minus x power 4 by 4. Now we need to find y of root 2, right? So y of root 2 is equal to root 2 into e to the power minus root 2 the whole power 4 divided by 4, which is equal to root 2 into e to the power minus of root 2 the whole power 4. Root 2 the whole square is 2. 2 2s are 4. We get 4 by 4. 4 cancels each other. We get root 2 divided by e. Y of root 2 is root 2 by e. We get root 2 by e. So the fourth option is the correct answer. The next problem, solution for lambda is equal to minus 1 and lambda is equal to 3 for the integral equation y of x is equal to 1 plus lambda times of integral 0 to 1 k of x comma t into y of t dt. Now we need to substitute k of x comma t. It is varying from 0 to 1. We need to find the range of t not for x. So I'm going to replace x by t, 0 less than or equal to t less than or equal to x. and x less than or equal to t less than or equal to 1. So this will give us cos hx sin ht, and this is cos ht sin hx. Y of x is equal to 1 plus lambda times of integral 0 to x cos ht sin hx into y of t dt, and then plus integral lambda times of integral x to 1 cos hx sin ht into y of t dt. So we solve by the method of Leibnitz rule. So y dash of x is equal to, here we have lambda outside completely, integral 0 to x. Differentiation of this will give you cos hx and then cos ht as it is, y of t into dt, plus the upper limit part, which is cos hx sin hx into y of x, plus cos hx sin hx into y of x. And this integral will give us plus integral x to 1. Differentiation of cos hx is plus sin hx sin ht into y of t dt, and the upper limit part will become 0, lower limit part will give you the solution minus of cos hx sin hx into y of x. Now you can cancel these two. You will be left with y dash of x is equal to lambda times of integral 0 to 1 and this part again. So integral 0 to x cos hx cos ht into y of t dt, plus integral x to 1 sin hx sin ht into y of t dt. So again taking differentiation, y double dash of x is equal to lambda outside integral 0 to x, differentiation of cos hx is sin hx into cos ht into y of t dt, and this part upper limit part will give you plus cos hx, and this is also cos hx, so cos h squared x into y of x, and the second integral will give you integral x to 1, differentiation of sin hx is cos hx, and this as it is sin ht into y of t dt, and the upper limit part is a constant, so this will become 0, and the lower limit part as it is, so this will give us plus sin h squared minus sin h squared of minus sin h squared x into y of x. So when you just combine these two, you can take out y of x from outside. Cos h squared x minus sin h squared is equal to 1. So we get y double dash of x is equal to lambda times of integral 0 to x sin hx cos ht into y of t dt, plus integral x to 1 cos hx sin ht into y of t dt, and this part taking y of x outside, you will have cos h squared x minus sin h squared x, and this part cos h squared and then sin h squared x, this part will give you 1. Okay, and this is what your question is, lambda times of integral 0 to x cos ht y of t dt. So this is the question, y of x is equal to 1 plus lambda times of this completely is present. So therefore, this can be written as y of x minus 1. So we can have this part to be y of x minus 1. So y double dash of x is equal to, this is y of x minus 1, and this part is plus lambda times of y of x. So y double dash of x is equal to lambda plus 1 times of y of x minus 1. First lambda value is given to be lambda is equal to minus 1. When I substitute lambda is equal to minus 1, y double dash of x is equal to minus 1. I should arrive at y double dash of x is equal to minus 1. When you see the third option and the fourth option, here this is what your first for y lambda is equal to minus 1, your y of x is. For lambda is equal to minus 1, your y of x is, right? So here when you differentiate this part, you should arrive at minus 1. But when you see here, x squared divided by 2 plus 3 by 2 minus tan h1. Here also the same thing is present. So x squared, we have the y of x is equal to x squared by x squared by 2 plus 3 by 2. x squared by 2 plus 3 by 2 minus tan h1, right? So this y dash will give you 2x by 2 as it is. Y double dash of x is equal to 1 and it is not equal to minus 1. Therefore, the third and the fourth options are wrong. These are wrong. And you will find this 1 and 2, either of them is true. We will also find for lambda is equal to 3. Now, when I put lambda is equal to 3 here, what will happen? Y double dash of x is equal to 4 times of y of x minus 1. This is what we need. Now, here the given solution y of x is, for the first option, 1 by 4 into 3 cos 2x divided by cos 2 minus sin 2 into tan h1 plus 1. Everything is constant over here. Only this 3 cos 2x is the variable. 3 cos 2x is the variable. Here in the second option, we find 1 by 4, 3 cos h2x. Here simply cos 2x and here cos h2x. We will verify. For the first option, for the option A, we have y of x is equal to 1 by 4 into 3 cos x divided by cos 2 minus 2 sin 2 tan h1 plus 1. So when you find y dash of x, this will be 1 by 4 as it is, and this denominator as it is cos 2 minus 2 sin 2 tan h1, and this part will vanish because it is a constant, and this will give you minus 3 sin x. And y double dash of x is equal to minus 3 by 4 outside. The sin x differentiation is cos x divided by cos 2 minus 2 sin 2 tan h1. Y double dash of x is equal to 4 times of y of x minus 1. So 4 times of y of x minus 1. Y double dash of x should be equal to 4 times of y of x. So here 4 times of y of x will be equal to 1 by 4 multiplied by 4. These two cancels each other. We'll have 3 cos x divided by cos 2 minus 2 sin 2 tan h1, and then plus 1, and we need to do 4 y of x minus 1. When you substitute here, my plus 1 and minus 1 vanishes. So we should be left with 3 cos x divided by cos 2. But here we have a negative outside and also a 4 which is disturbing us. So this option is totally wrong. First option is wrong. So first option is wrong. We will verify the second option. It must be the correct option. 3 cos 2x, right? So here y of x is equal to 1 by 4 into 3 cos hx h2x, 3 cos h2x divided by cos h2. What is the question here? 3 cos h2x cos h2 minus 2 sin h2 tan h1 plus 1. Y dash of x is equal to 1 by 4 into 3 times of sin h2x. You will just multiply this 2 here, multiplied by 2, divided by cos h2 minus 2 sin h2 tan h1, plus this part is a constant, so it will vanish. Y double dash of x, which is equal to 1 by 4 3 cos h2x, and this is 2 into 2 will give you 4, and this 4 and 4 cancels each other. Cos h is it minus 2, sorry, h2 sin h2 tan h1 everything. Yes, y double dash of x is actually equal to 4 times of y of x. What is your y of x? This is 1 by 4. 1 by 4 and 4 cancels each other. We have cos h2x divided by cos h2 minus 2 sin h2 tan h1 and then minus 1, right? So plus 1 minus 1, they both cancel each other. We get the answer. So the second option is the correct answer. This is the correct answer. Thank you.